Lesson 61 is probably not like anything you've learned in math before. It may not even look off firsthand like math. It's really just about ordered lists, but it does get into typical arithmetic by the end here. You might find it fun, you might find it mentally exhausting, or maybe even just frustrating, but I think this lesson is really important, and you will get it, whether it's not today or tomorrow, but you will get it. I would say it's a moderate difficulty because it is so new. A sequence, I mean, is a word you're going to use in all walks of life. It's just an ordered list. And in math, that's going to mean it's an ordered list of numbers. We call numbers, when they're in a group like this, terms. And terms in a sequence will follow a certain pattern or rule. Check out 3, 6, 9, 12, and the ellipse means it keeps going. What's the pattern? What's the rule? We got 4 terms. We have to guess what's the rule of the sequence going forward. And maybe you could even guess what's the next number, kind of like we do on a map test or something. It's pretty common, guess the next 2 numbers in the sequence or something. In this case, it looks like they're adding 3 every time, right? 3 plus 3 is 6. 6 plus 3 is 9. 9 plus 3 is 12. So the next 2 numbers would be 12 plus 3 is 15. And 15 plus 3 is 18. So 15 and 18 would go next, and then 21. So each term is plus 3. Another way to think of that is there's a constant difference. If you take, let's say, the third number, 9, and you subtract the second number, 6, you would get 3. And every time you do that, every time you subtract the next number from the previous number, the previous number from the next number, you get the same. You get 3. It's a constant, consistent difference between a term and its previous term. So you could look at it either way. You add 3 every time, or you could say there's a difference of 3 between each one. Difference or added. But we call that an arithmetic sequence or arithmetic sequence. An arithmetic sequence has a constant difference between terms. Example 2. What's the rule? 1, 3, 9, 27. Obviously, we're not just adding 3. And it's not even a constant difference, because what's 3 minus 1? It's 2, right? But then what's 9 minus 3? Is it a constant difference? This one was 2, but this one was 6. So that's not an arithmetic sequence. Certainly not this one. What is that? 18, I think. Let's go with it. So it's not an arithmetic sequence, but maybe you've already guessed what it is. We multiply by 3 every time now, right? Multiply by 3, multiply by 3. So 1 times 3 is 3. 3 times 3 is 9. Basically what we're doing is the multiples of 3. Well, actually not, because as soon as you get here, it's not a multiple. We missed 12 and 15 and 18 and a bunch in between. So we have to multiply it by the previous one, which makes it grow really fast. So it's not just the multiples of 3. It's not just 3 plus 3 plus 3 plus 3. That would be the previous one. In this case, you have to multiply by 3, but now it's 9 times 3 is 27. 27 times 3, not 3 times 3 and then add it. You got to multiply that number by 3, and you get 81. And that's a geometric sequence, where we multiply by a consistent number every time. Or again, another way we can think of it is, if you divide a number by the previous number, you will always get the same quotient, 3. Or you can think of it as a ratio. The second number over the first number is 3, just like the third number over the second number is 3. And the fourth number over the number before it, the third number, is 3. So it's always 3. It's a constant ratio. You're multiplying by the same thing every time. So hopefully you follow that pretty well, or you'll get it. Now, this is really important, but it might be where it starts to get a little bit deeper. The terms, I've been talking about them, the second, the third, the fourth. That's its position, where it is in the list. It's the first number, it's the second number, it's the third number. And sometimes we abbreviate that with just the letter N. It's its number in the list. The number. 3 What if 3 is the first number? And what if 6 is the second number? Then its n is 2. And 9, its n is 3. 12's n is 4. So this actually is a different list because 1 isn't on here, right? We start at 3. 3 is the first number of the term. So this list would look like this. 3, 6, 9, and so on. 12, 15. That's its number, its position. I'm going to call it its number from now on so we don't get confused. Now, what's the value? This was the number. Value, we abbreviate just maybe A. Value is the number itself. It's worth 3, or it's worth 6, or it's worth 12, whatever. And that's literally what the list looks like. The value is the numbers themselves, and then the n, maybe I should switch colors. The n of these numbers is 1, 2, 3, because it's the first, second, or third number in the list. Kind of make sense? So if we know both the number and the value, the n's and the a's, we can represent it in the graph. Meaning, if we have a list like this, 3, 6, I shouldn't say list, I should say sequence, 12. If I have this sequence, okay, what's also true is, okay, that's the A. The N is 1, 2, 3, 4. First, second, third, fourth term. If we use this as the X and this is the Y, we can graph it. First term, so 1 over, worth value is 3. 1, 2, 3. Goes right there, right? 1, 3. Second term, up 6. The third term is worth 9. 3, 9. And you do that where your X is first, second, third, fourth, fifth in the list. The Y is the value. Geometric sequence is going to grow very quickly because the first number maybe is 1, but then the second number, it's being multiplied. So suddenly we get this big jump, even bigger jump here because we're multiplying by 3. That's what geometric meant. So the first term is 1, second term is 3, pretty normal. Actually, he's growing slower right now than the arithmetic sequence. But then jump to here because we're multiplying by 3. So the third term is 9. That's where we get that. 3 is the n, or the x. 9 is the a, the value, or when we graph, it's really the y. Okay? If you have to write a formula, which you don't have to do in the practice, but you might have to do in homework, write a formula that describes this sequence. So the values are 3, 6, 9, 12, right? 3, 6, 9, 12. That's the a's. Its number is always 1, 2, 3, 4. So the formula we see that the value A, right? A is 3 times its number in the list. They show it like this, A with an n subscript. It means the value of the nth term, okay? So just remember we write the formulas like this. Go like this, and then in this case, each number is 3 times its position, 3 times n. And in this geometric sequence, it gets the most complicated. The value of A, first we make the table, 1, 3, 9, 27. We actually take 3 and we grow exponentially. The exponent is 1 less than its position, n minus 1. Meaning, if I want to know what is the fifth number, what goes here, okay, what is the fifth number? What's the value of the fifth? I take 3, the constant ratio, and I go position of 5, but 1 less. 3 to the 4. So the fifth number is worth 3 to the 4th, according to this equation, this formula. So 3 times 3 times 3 times 3 would be what this is, which was, what, 81 times 3 was like 243 or something like that. Here, I'll do it quick. Let's just go like this, times 3 times 3 times 3. Oh, that was just 81, sorry. So we found out that this number is 81 by taking 3 to the 4th, because that's 1 less than its position of 5. Okay? That's harder than most of these. You, how about you just do C, D, E, and G. Okay, and you don't have to write any formulas. You just have to go, so we're doing C, D, E, G. In this case, you're just writing the first 4 terms of the sequence.